let you on internet. I also thought about talking about 3-level systems, but I think Irina has done it much better than me, that I would have done. So anyways, I have let some calculations which are from a different point of view as hers. I have calculated, so I have done detailed calculations for the two photon transition rates and etc. If you want, you can take a look, but I'll not talk about this. So I'll just end on the cooling and trapping. And so maybe we'll end a little, I don't know, I think maybe it's not going to take 1 hour and a half, I hope, but in the end I always take 1 hour and a half, so I don't know if I'll really be able to let you go earlier. And then we'll stop, and then we'll have Helene's seminar, okay? Before you can go to the weekend in São Paulo and get ready for the next week. So in the last session, we discussed about we saw how to cool the atoms using radiation pressure force, right? So we have seen 2 different schemes. One scheme which was Siemens lower, which was suitable for cooling an atomic beam, and another scheme which was the optical molasses, which was suitable to really try to bring the atoms to kind of small temperature. But if you remember what we have deduced as forces, all forces were dependent on velocity. No force was depending on position. So up to now, we have no trapping scheme, okay? You can show that if you just send light beams in different directions of space with fixed detuning, you cannot make a trapping force in all 3 directions of space just with radiation pressure force. Now, of course, we'll be able to trap them with dipolar forces. This is another story, but you cannot do this. So you must be smarter if you want to use use radiation pressure force to trap atoms. So what you can do is you can enjoy, one of the most common strategies is enjoying the fact that the atomic resonances can be modulated by magnetic fields to create a special modulation of the light force. Okay, so now we're going to use the special modulation of the resonance that the Zeeman effect can bring to make special modulation of the light force that the radiation pressure can make. So how do we do this? Again, we're going to make a 1D model for the MOT, which is already there. So the idea is that we're going to apply, let's imagine in this 1D model for magneto-optical trap. Let's imagine that you are applying a magnetic field which is like small b, z in the z direction. This means that you're not applying now a constant magnetic field, you are applying a gradient of a magnetic field with a gradient, right? So if I draw the magnetic field, this is going to be the magnetic field. B is just the slope. Small b is just the slope now, right? So if you do this, you see now what's going to happen to your laser to the frequencies of each one of the transition. If I put 0 here, what we have is that let's place ourselves in a simple situation again, a transition from j equal to 0 to j equal to 1 level, and so this means that the ground level is not shifted. The ground level is not shifted by Zeeman effect, but each one of the excited levels that we can call E-1, E0, and E1, they are shifted by Zeeman effect. So the 0 level is not shifted, but the +1 level is, and the +1 level has an energy which is proportional to the magnetic field. Okay, I mean, this depends on the value of the Londe factor. So because the splitting is the Zeeman shift is just equal to that. You can have lambda effectors which are negative. They are not very usual, but it happens. But let's assume that this is positive. So just for being easy here. If it's negative, you should just invert the sense of the magnetic field and everything will work just fine. So, and then the -1 is proportional to minus the magnetic field, so you're just going to be shifted in the other way. So you see what I'm drawing here now, those are the energies or the frequencies of each field, each level is a function of position. So what we got now, we got a modulation of the energies, right? So the energies are modulated as a function of the position. So I want to enjoy this to make a trapping force. So how do I do? First, my magneto-optical trap, I want it to trap, but I also want it to cool. So I am going to send laser beam in two opposite directions. So my atom is here. I'll still do the same scheme as for the molasses. So for keeping the cooling force of the molasses, I still want to keep the detuning negative. So I will be using delta 0 smaller than 0 as before. Okay, so this means that if I draw now the resonance with my light here, this is going to be omega. So omega is smaller than omega 0. This is omega 0, right? Omega 0 is the resonance. So let's say that I'm plotting E divided by H bar. So here omega 0 is the resonance of the unperturbed level, and omega is the frequency, which is smaller, so delta 0 is smaller than 0. I do this again, I do this in order to preserve cooling. So this is for having cooling. Because then I have that beta parameter bigger than 0, right? I will still have here a force which is dependent on the velocity of my atom. Okay, so I just have the same thing. But now, I have additional component now, because you see, I have the resonance is dependent on the position also. So if you go to the expressions, this light beam here has wave vector k plus, this light beam has a vector k minus, and this light beam is making a force which is F plus. This light beam is making a force which is F minus, and the expressions for the force are really the same, but now we need to add a new ingredient, which is the Zeeman effect. So now the force F plus, if you go to the expressions that you had there, is just going to be the same, it's plus gamma divided by 2 so gamma divided by 2, S0 divided by 1 plus S0 plus 4 over gamma squared times the detuning, which is delta 0. And then we had minus KV, it's a minus, right? It was a minus here, but then we need to add the detuning due to Zeeman effect. And this detuning due to Zeeman effect is depending on the polarization that I send. So I need to be smart. For this beam here, I want to send a polarization sigma plus. And so if I send a polarization sigma plus, I need to add that the omega 0. So this is omega minus omega 0, but omega 0 now is omega 0 plus this term here. So I end with something which is like this, minus this. Right? So mj equal to plus 1, I end up with this. Let me just check if this is correct. What? Square, yes, of course, thank you, squared. Okay? And then the force created by the other one, it's going to be in the opposite direction, so minus wave vector k. Then the Doppler is also going to be different. And then I'm going to put polarization sigma minus. We're going to understand why in a second, sigma minus. And then I also invert this. So why I'm doing this? Look, I want this beam here to, so if I want a trapping force, I want this beam to act more on the atoms that are coming to this side, right? Because they are coming here, and then I want them to be pushed back. So I want this beam to be resonant so this beam, since the detuning is small, the detuning is negative, this beam has a chance of being in resonance with this transition, but for that I need to talk to the level plus. So this means that this polarization must be plus. And so this beam will be resonant with atoms in this position here, and the further the atoms are, the further away we are from resonance. And I'm going to ask for the opposite here. This beam, I want to push the atoms when they are too far in this direction. So I will arrange myself for the beam. So I can do this if I arrange myself for this beam to be resonant with that transition here. So then I'm going to send sigma minus, because this is the minus one. You see? So then what's going to happen is that I'll have just the same kind of graphic if I do the global force, which is F plus plus F minus. If I sum both forces, and if I draw them here, let's put this as 0, and let's draw the simple case of an atom at rest. For an atom at rest, I just remove this here, and I'm going to have the same behavior as I had for velocity, but with respect to position. Oh, I'm sorry, the magnetic field, where is the position I should put? Magnetic field is small b times z, right? So this is z now, because I have a gradient of magnetic field. And so when I put this, the same thing I had for velocity, I'm going to have now for position. I will have the beam coming in that direction, resonant for some position here, which is z, I'm calling this minus z resonance, and this is plus z resonance. And so we're going to have something like the F plus is this, the F minus is that, and then the total is like this. Okay. So which kind of force? This is 0. Okay, I can, to make it easier, I can put it like that. This is 0 position. So which kind of force I have close to the center is of the minus kappa x, or minus kappa z. So which kind of force is that? Restoring force, right? Derives from a potential. So this derives from a kind of potential, which is kappa over 2 z squared. This is just a kind of harmonic potential that I created in the center, right? Now, the force, again, is not purely conservative. Why is not purely conservative? For several reasons. First, I see that I still have this v here. So if I linearize this force with respect to z and with respect to v, I'm going to find that still this term here. So the total force is actually like that. Okay? I have a dissipative component that cools the atoms, but now I have a trapping component that traps the atoms, a restoring force that traps the atoms. Okay? And second, it's not conservative because you have spontaneous emission, and of course you have some fluctuations, and this force is not conservative. But I can make appear a kind of potential here, okay? So in the end, this is the principle of the magneto-optical trap, which is really simple principle. Of course, things are more complicated when you don't have a j equal to 0, j equal to 1 transition. You can have more levels, can be more complicated, but the basic principle is the same. In particular, the choice of polarization is the same, but again, when I'm talking about choice of polarization here, I am considering the same quantization axis. So I'm saying that I need to send opposite polarization with respect to the same quantization axis G. But if they have opposite polarization, but they have opposite propagation direction, this means that those beams have same helicity. If I put my polarization detection here and there, I'm going to find either R or L for both of them. Okay, so it's the same polarization with respect to the propagation direction. So you should be careful. This is very confusing in the lab. Everyone is discussing and lots of fights and every time, yes. But in the end, they need to have the same helicity in this situation here. So same pair of beams, same helicity. But opposite polarization if I consider a fixed quantization direction. Okay, and if you can linearize this force in first order in Z and B in V to obtain kappa and beta. Beta is going to be just the same, and kappa. So kappa is going to be just as beta, you see, but you need to go to beta and replace 1k by this expression here. And in the end, you're going to have your kappa. I can write the kappa. The kappa is just going to be equal to this. Okay? So you understand, because I'm going to do the same kind of linearization, but here I have a different coefficient. So I can just calculate like this, and if you go to the expression for beta, you're going to find kappa, okay? So, again, so if I ask you, what's responsible for the restoring force in a magneto-optical trap? Radiation pressure. Who's responsible for the dissipative force in the magneto-optical trap? Radiation pressure. So all the forces are done by light. It's radiation pressure. You don't have magnetic forces here, okay? So you can have magnetic trapping, we're going to discuss in a second, but this is not magnetic trapping. In a magneto-optical trap, what does the magnetic field make? It just modulates the resonance. Just modulates the resonance for the radiation pressure to have kind of restoring component, okay? But everything here is radiation pressure, okay? And then, so this is more or less what's drawn here. And then as I show you, so since this is based on radiation pressure, when you do a magneto-optical trap, you really see the atoms shine. And typically, the lifetime of a magneto-optical trap is not very long. So what you are seeing here, the beams must be turned on continuously. If I turn off the beams instantaneously, of course, the light will turn off instantaneously because you don't have any more light coming, and then the atoms will quickly go away. And even if I let the beams on, but I cut the atomic source, let's say I have some atomic beam arriving, and then I close this atomic beam, in a few milliseconds you're going to lose all your atoms because it's a very dynamical system. So the number of atoms, the static number of atoms in a magneto-optical trap is an equilibrium between what you can put per second and how much and a loss rate, which is typically several hertz or maybe kilohertz, okay? So those are stationary magneto-optical traps in different colors because depends on the transition, okay? But here, up to now, I have just made a simple model for a 1D magneto-optical trap. Now you can imagine that you can, as we did for the molasses, you can have 3D magneto-optical traps. You just apply magnetic gradient in the 3 directions of space, you put your beams in the 3 directions of space, and you get your magneto-optical trap. Now, how do you make a magnetic field gradient in the 3 directions of space? The most common and widely used strategy is to use what we have there, the coils in the so-called anti-Helmholtz configuration. So what is the anti-Helmholtz configuration? First, what's the Helmholtz configuration? What do we call Helmholtz configuration for the magnetic field? Yeah, so the Helmholtz configuration is you take two circular coils of radius r, you make some current here in the same, this is for Helmholtz, in the same direction, and then the distance of your coils is r or 2r? 2r, right? 2r. R for Helmholtz, thank you. So you know that for the small, I have not said this in the beginning, but you know that everything that I'm saying here, so Elena taught me. So I'm feeling very stressed here in front. But if I say some mistake, you should go and talk to her. Okay, so this is R. And then what's interesting about, this is not what you use for a MOT, but what's the Helmholtz configuration? The Helmholtz configuration, you put you put the current in the same direction, and then here you have a constant magnetic field, and the quadratic term and the third order term is equal to 0, and just have a fourth order term, so the magnetic field is really stable. You can make a really nice magnetic field. When you have the two coils with the current running the same direction, but you don't have R, the distance equal to R, we call this quasi-Helmholtz configuration. You still have a constant magnetic field, but then you have a quadratic term now. This is quasi-Helmholtz. Now, the anti-Helmholtz is R or not R, we don't care. We call anti-Helmholtz whenever the currents are in opposite direction, and you can have a circular, or you can even have a square coils. We're going to say anti-Helmholtz configuration, and this is anti-Helmholtz configuration. And then the anti-Helmholtz configuration, what happens? So how is the magnetic field? So the magnetic field can be complicated, but what interests me is the magnetic field close to the geometric center of the coils. Okay. So if I put some axes here, x, y, and z, you see. So by symmetry, what happens if here I have put the current to run like this? You see that the magnetic field enters the coil. But here also the magnetic field enters the coil in this direction. Okay, so by symmetry, what will these lines do? They will need to avoid each other. So this is what happens, and this happens in all the circle, because this particular situation have circular symmetry. So the magnetic fields are drawn like there. I have taken this from an article, you see. So the lines enter like this and enter like that. If you invert the sense of both coils, you can just make invert the sense of the magnetic field. So they can enter or they can go out. Okay, right? So you have some symmetry. Now, how is the magnetic field close to the center? So by symmetry, the magnetic field really in the center is 0. So the magnetic field as a function of x, y, and z close to the center is 0. And then you see, by symmetry, if you approach really in this line here, the magnetic field must point in the z direction. Here, the magnetic field must point in the y direction. In each direction that I approach, it points in the same direction. So I'm going to have something which is like just like a bx in the direction x plus by y plus bz z ez, correct? Now, by symmetry, you see that bx must be equal to by, because you have symmetry in x and y. So this is just, I'm calling this br. Okay? And then there's another relation between br and bz. The relation is given by electromagnetism. Oh, right? So if I take the divergence of this, is just derivative of the x component with respect to x, so in the end you get br plus bz equal to 0, and then you get br equal to minus bz divided by 2. So then the field just is very simple and just depend on one parameter, which is the gradient in the z direction. So the gradient in each one of in x and y direction is equal to half of the gradient in the z direction and in opposite direction, with opposite sign. So then I can just write the field like b, that minus x ex over 2 minus y ey over 2 plus z, ez. This is the field around the center. So you see that you can have a gradient in the x direction, in the y direction, and the z direction, okay? But then now you need to think, so the helicity of the beams in those directions are the same, and the helicity on those beams is inverted. So I don't know, you need to think. Normally you put this and you try, it does not work, you invert everyone and you try, it works, okay? So this is what you should do. Okay, so this is a 3D magneto-optical trap, and in this way you can trap your atoms. And of course, all the reasonings that we have done before for cooling, so you want the detuning to be around minus gamma, you want minus gamma for alkaline earth. So if you have hyperfine structure, you have some Sisyphus cooling, you prefer going closer to minus 2 gamma, minus 3 gamma. Intensity, you want to saturate, but you don't want to, you want to have some intensity, but not to saturate that much. So this gives you more or less where you should be. But in the end, what you must do, you have all the knobs, and you turn all the knobs, and you stay where you want. So you want less temperature, more atoms, better phase space density to begin your cooling process. Okay, so you get this optimizing everything. Okay, depends on what you want. Okay. So all those traps, this is the only trap we have seen, so this is the first trap. This trap is not conservative. Okay, so it's nice because you cool and you trap, but it's not conservative, so for lots of physics, you cannot really do there. So for doing a quantum gas, for example, quantum gas, so Hélène cannot do a quantum gas in the magneto-optical trap. So she needs to do better than this. So then you need to move to a conservative trap, okay? So also a purely conservative trap. So purely conservative trap, it's going to be hard to do with radiation pressure force. So you can try to do with dipolar force. This is going to work, okay? But you also have another strategy that we can discuss before. So something that you can use is magnetic trapping, okay? So magnetic trapping. What does it mean, magnetic trapping? Now I'm going to use purely magnetic fields. So for magnetic trapping, okay. So we will be using the Zeeman Hamiltonian. Okay, so the first approximation that you can, not approximation, but the first consideration that you can do for the Zeeman Hamiltonian is that, let's imagine that an atom is in a certain position with a magnetic field pointing in a certain direction. So normally what you have is that then the energy levels of the atom are splitted following that quantization axis, okay? So now, imagine that you have another atom in another position. So the direction of the magnetic field can be different. Then the levels are different. And the levels in this quantization direction are linear combination of the levels in the other quantization direction, you see? So in general, depending, if you know what are the eigenstates of the, if you apply a magnetic field in the z direction or in the x direction, the eigenstates are going to be linear combination of the one of the other. So now imagine that an atom is moving in this landscape with magnetic field that can have the direction changing. Well, in principle, if the atom is in one state here, this state is a combination of the eigenstates on the other position. Now, if the atom do not move that fast, or if the magnetic field seen by the atom have its direction moving slowly enough, and the enough is a condition that you can establish, we're going to say that the levels, the magnetic sum levels will continuously deform into the magnetic levels of the other situation. And then, since they are all separated in energy, you will be following in the same energy level, and you will not be mixing, but you'll still stay in the same energy level. So if you are in the +1 here, you continue to be in the +1 there. So this is called adiabatic. So you are adiabatic, transferring your atom from one level to the other level. Why this does not work every time? So this does not work if the movement is too fast, and too fast is something comparable to the energy difference, because if the energy difference becomes too close, you can also have some kind of crossing. So if they are far away, it's harder to cross, and if it moves fast, it's easy to cross. If it moves slow, it's hard to cross. So you have a kind of condition, a adiabatic condition that I'm not going to write, but in the end, if this adiabatic condition is fulfilled, not every time it's fulfilled, I'm going to say when it's not fulfilled, but if it's fulfilled, you can write this every time as minus the magnetic moment operator times the modulus of the magnetic field, because then you are always with your magnetic moment pointing to the same direction of the magnetic field, because of this adiabatic transformation of the levels as the atom moves around. Now, if I have, for example, a magnetic field like this. I can try to do a kind of trapping, is maybe the easiest thing I can do. With a magnetic field like this, how it works? So this is, I know that I can just write this as mu B, GF, MF, and B, which is modulus of that field. So this is gonna make me mu B, GF, MF times, what's the modulus of that field? So it's square root of each component squared. So this is square root of, so the B, small b I can put here, times the square root of x squared over 4 plus y squared over 4 plus z squared, you see? So this is a kind of potential, which is depending on the value of GF and MF, has a minimum in the x, y, and z equal to 0, or has a maximum in x, y, and z equal to 0, okay? So for example, if my atom moves in the x and y equal to 0 and moves in the z direction, let's suppose that GF is positive. If GF is positive, the MF equal to +1 is going to see something like this. So this is the energy as a function of z for MF equal to +1. If you have let me draw not that big because I want to put some more. So MF equal to +1 does like this. If you have MF equal to +2, it's gonna be like this. If you have MF equal to 0, just see nothing. And MF equal to -1, and -2, let's say you are in F equal to 2 level of rubidium, is like this, okay? So some magnetic levels are trapped, some are anti-trapped. This is if GF equal to 0. This is, for example, F equal to 2 for rubidium. If you go to F equal to 1 of rubidium, the JF is negative, and then it inverts. So you can trap the -1, and you anti-trap the +1. So then depends, you need to know also your Londe factor. You need to calculate your Londe factor, okay? So this is, you can do a trap like this. Wow, it's nice because you already have your coils that you use to do your mod, so you just let them on or you increase the current, I don't know, and you do your magnetic trapping. This is nice. But there is some a disadvantage. What's the disadvantage? Well, if your atoms are hot, not that much, but if your atoms, you begin to cool down your atoms, I don't know, via evaporative cooling, what's gonna happen is that here, close to this point here, you see, so when you pass from here to there, the magnetic field is passing, the magnetic field in the z direction is passing from pointing one direction to pointing the other direction. So if your atom traverses here, the atom will see a magnetic field that has discontinuously changed direction from here to here. So the condition of a diabatic following is not gonna work. And so the atom will pass there and will turn. So atoms that are here are the colder. When the atoms are here, it's because they are cool, because if they are hot, they are occupying all the potential, and if they are cold, they're occupying here. So for a cold cloud, you begin to have some losses. The atom, which is in the +2 level, will flip and become -2, and bye-bye atom. It will just go away. You see? So this opens a kind of hole in your trap. This is called Majorana hole. Okay? And because those losses are called Majorana losses, you can calculate them, etc., etc. This is not good. So then you can think, okay, but can I do better? Can I trap my atoms close to a minimum of magnetic field, but not a zero of magnetic field, right? So can I have a non-zero magnetic field here? So you can, and you have some strategies, and some strategies. So you have several trapping strategies to make a minimum of the magnetic field, which is not zero. You cannot have a local maximum of magnetic field due to a theorem called the Earnshaw theorem. I have a reference in the notes if you want to check. But you can have a minimum which is not zero. And also the strategies are called, so you can have the IOFE Pritchard kind of trap. You can have what some people call quick trap, is another strategy. So you have a Pritchard trap, you just, more than your coils, you put you put also some rods that creates an additional quadrupolar field. So you needed to have, so this is wrong, this is like this and like that. And so with this kind of, with additional currents here, you can lift the zero of your magnetic field. Quick trap is another strategy. You can also do what people call a plug trap. What is a plug trap? Is this kind of trap, quadrupolar trap, but then you put some repulsive optical dipole trap in the middle, so then the atoms never get there, and then in the end, what this makes several potential minima, 1, 2, or a ring of potential minima. Then you need to deal with this, but it's possible also. If you move a little like this, you have just one potential minimum, okay? So you need to avoid this if you want to cool your atoms in this trap, okay? So, but you can do magnetic trapping also. And of course, you can do dipolar trapping. This is why you have deduced the optical dipolar force. And then, for the optic dipolar trapping, you have a zoology of traps. And you have a zoology of traps because, remember, what's the principle of optical dipolar trapping? Well, for optical dipolar trapping, you just have a potential which is proportional to the intensity, right? So I need to get back to the potential. That must be somewhere far away. So okay, so for optical dipolar trapping, you have a trap that if you are red detuned, means that if the frequency of your light is to the red of the transition, you'll be trapped to the maximum of intensity, right? So you trap the maximum of intensity. The maximum of intensity means a minimum of potential. And you can have light beams and light fields of very different shapes today. This means that you can have very different geometries for doing optical dipolar trapping. So I have just made a small list of things that you can do here, and I think it's not. I'm pretty sure it's not exhaustive. So to begin with, I'm gonna turn off the light. Some recognize the images. So what you can do, you can just, let's say I'm gonna send one beam, right? I'm gonna trap my atoms, I send one beam. So one light beam has a intensity profile. It's Gaussian. So if you cut the beam like this, you see a Gaussian intensity profile, right? And the light beam, a Gaussian light beam. So if you write the intensity profile of a Gaussian light beam, so I don't care anymore. I don't care about the phase of the Gaussian beam because I just care about the intensity for my trapping. So I'll just write the intensity of a Gaussian beam. So the intensity of a laser beam. The simplest form, I can make it more complicated, but the simplest thing is just a Gaussian. So this is just central intensity times e to the minus 2 whole square divided by a parameter called the waist of the beam. So here I'm assuming a beam that propagates in the z direction, okay? Divided by waist z squared divided by waist in 0 squared. And this is all. what's this parameter here? The waist. The waist is is just the radius of the beam. You see, so the beam has a rho here is square root of x squared plus y squared. So you see that for a fixed z, the profile of the beam is a Gaussian, right? And as the beam propagates, you have the waist of the beam, so the typical transverse size of the beam that changes. The minimum value is W0, and then this is going to be W0 times square root of 1 plus z over zr squared. If the focus is at 0, zr is called the radial range. It's just pi waist at the focus squared divided by the wavelength of light. So this means that the waist as a function of z is just kind of hyperbola, right? The minimum waist, the minimum radius of the beam is W0, and that this beam will stay collimated for a typical distance, which is the radial range, right? So you see that the radial range depends quadratically on the waist. So the smallest the waist, the smallest the collimation length, and the highest it will diverge, because then this is going to be in the long here far away from the focus. This evolves like waist 0 times z divided by zr. So the smallest the zr, the fastest it diverges. Okay. So okay, all right. So this is a light beam, and so you see that you can trap the atoms in the light beam. Now there is just one laser beam there, and what you see is in false colors. Why in false colors? Because now this is a conservative trap. You don't really get to see what's going on. The atoms can be there for seconds, but you will not see them because they are not scattering light anymore. So in order to see if you have atoms there, what you need to do, at some point you need to send some light, resonant or almost resonant, and you need to see the scattering light, or you need to send some light, let the atoms absorb, and see afterwards the shadow that the atoms make. So you have some techniques to see if you have atoms. And so there is just okay, so you do some kind of imaging, probably absorption imaging here, and then you can see your atoms, right? So this is an imaging false color there. Now, okay. I don't care. So, okay, so once you tell me something, you can talk. Yeah. So do you understand how this is like that? Why this is like that? Where is the focus of the beam? Must be in the maximum of the atoms, right? Because you see, so if your beam is most focused here, the intensity in the center is something like this, and if we go far away, the intensity is more spread, so it is larger and less deep. So you have some trapping here, but you also have some trapping here. It's just that the trapping in this direction, the length scale is given by the waist of the beam. Now the trapping in the longitudinal direction, the length scale is given by the radial range. So of course, if you send just one beam, your cloud will be much more elongated in the direction of the beam propagation than in the other two directions. Okay. So, but then you can do better. You can do what's happening here. What's happening here? You do what we call a cross dipolar trap. You cross two beams. Okay. So now this is better, because if I cross two beams, one beam is a potential, the other beam is a potential, and in the crossing of both you have a small potential. Well, now you can trap in three directions, and you can have something which is quite symmetric. You can arrange yourself to have something which is quite symmetric. Okay. Very well. And this is and you can have some cloud which is quite dense. So there I'm just showing an image of a cloud that we produce in our lab. the optical depth in the center is 90. Now, of course, to measure this optical depth, you should not shine a resonant light. This is for some phase contrast imaging, but you can see, you can trap lots of atoms and you can keep them, and you can keep them for seconds if your vacuum is good and if you have no noise on your system, etc. Okay? So this is what you can do if you have optical dipole traps. Now, what? You can do better. Not better, it's not better. You can do different. Sometimes for what you want to do, it's great that you have your optical dipole trap, your cross dipole trap, and it's everything you need. Because what's going to happen? Something that I forgot to say. Which kind of trap is this? Now, you are trapping to the bottom of the intensity, and the intensity is Gaussian, so it's weird kind of trapping. But if you are close to the center, you can always do some kind of quadratic approximation, right? So it's not really a Gaussian trap. So what you have, every time this kind of traps, it's very simple to describe the trap. And this is why it's powerful also. You just need to know 3 numbers to know your whole trap. So which numbers are those? So, okay. Now, you see that if I put this profile here inside there, I'll just have something which is U is equal to a constant that I'll call U0. So what's U0? U0 is just all of that plus I0 times W0 squared. This is U0 for me, okay? And then times e to the minus 2 x squared plus y squared divided by WZ squared divided by WZ squared, okay? So this is basically what you have, constant times that. Okay, so now this is a function that has, and then I'm gonna just put, I'll just put a minus here, because for U0 positive, okay? Because delta star is negative, so I just put a minus here. U0 now is positive. I have a beam which is red detuned in order to do this trapping. Okay, so this is just, I can just do quadratic approximation around 0, okay? So UD is gonna be more or less minus U0, okay? Plus, I'm gonna write the first order term. First order term is just gradient of UD times R, but how much is this? 0. If you are close to the minimum, this must be 0, and then you end up with the second order term. Second order term, you can write it just as sum on E and J, 1/2 second derivative of UD with respect to XE and XJ times XE, XJ, okay? And so XE, you understand this notation. So 1 to X1, 2, 3 is X, Y, and Z. Okay. And this you can write, so okay, so then you have a constant plus that. A constant, I don't care. The constant is just the bottom. And then now, this, how can I write this? I can write this just as 1/2 times X, Y, Z. Oh, sorry, the opposite. This is line. So X, Y, and Z, a matrix, and then X, Y, and Z. Which one is this matrix? So this matrix is the second derivative of UD with respect to X, the second derivative of UD with respect to X and to Y, and etc., etc. You understood who is this matrix, okay? So this is a matrix that I'm gonna call M. What's nice about this matrix? What's nice about this matrix is that this matrix is symmetric. So here you mean? This. Yes, you mean here. This W0 squared here. Yeah, so my U0 is... it's not dimensionally equivalent, of course, yes. Yes, because dimensionally this is not an energy, of course, yes. Of course, it's right. Because then I can, yes, exactly, yes, okay. So then this is U0, really the value in the center, it's not the same. Yes, thank you. So W0 squared, And then, okay, and so this matrix here, this matrix is symmetric, right? Because derivative with respect to x and y and x, real and symmetric, invertible. So you can find 3 eigenvalues, 3 eigenvectors, right? And then 3 eigenvalues, 3 eigenvectors. I can just write this. If I do now, so imagine that I have found the 3 eigenvalues and eigenvectors, and I do a rotation on my basis to write this as in these 3 eigendirections, let's say, okay? So I'll have this x prime, y prime, and z prime, which are linear combination of x, y, and z, which are just pointing in the 3 directions. So because the 3 vectors are orthogonal also because it's symmetric matrix. So I can have those 3, and I can just write this as 1/2 of x prime, y prime, z. Let me write it there because this is going to be a little confusing. So in the end, you just have, you can approximate this as u equal to minus u0 plus 1/2 of x prime, y prime, z prime, and the matrix, which is now diagonal, I'm going to call this u x prime, u y prime, u z prime, 0, 0, 0, 0, 0, 0, x prime, y prime, z prime, okay? And this is just equal to minus u0 plus 1/2 of u x prime, x prime squared, plus 1/2 of u y prime, y prime squared, plus 1/2 of u z prime squared. And I just can exchange each one of those by u x prime equal to the mass of the atom times something which is a frequency. So if you remember the shape of the harmonic potential, you make here the frequency appear, and I'm going to do the same thing, and in the end you just end up with minus u0 plus 1/2 the mass of the atoms, omega x squared, x prime squared, plus omega y squared, y prime squared, plus omega z squared, z prime squared. And in the end, doesn't matter. You do what you want. Everything you want to know is the 3 eigen frequencies of your trap. So if you know the 3 eigen frequencies of your trap, you know your trap close to the bottom. Of course, you can, if the atoms are hot, they will explore some non-harmonic regions of your trap, and then things can be harder. But in principle, you're not doing this. And okay, so you need to know 3 numbers, okay, 4 numbers of your trap. The depth, u0, that usually you give in units of, usually you give the height of the trap in units of temperature. So normally everyone's gonna say, oh, my trap has a depth of 1 millikelvin. What does it mean? It means that kBt equal to that, and so this is the depth in Kelvin, in millikelvin. And also the 3 frequencies of your trap. Okay, and the x prime, y prime, and z prime are just the eigendirections. Now, for a trap like that, it's easy to guess the eigendirections must be the symmetry directions of your beam. So if your beam is elliptical, it's going to be the 2 axes of your beam and then the propagation direction. If your beam is circular, you have 2 equal frequencies and then the propagation direction. And here you are going to have, okay, then you need to figure out. You need to do the calculation. Okay, but the calculation is this. You just do the calculation and you figure out. Okay. So you just need to do this, you need to know this. And then those traps are harmonic. The traps you can do like this with 1 beam, 2 crossing beams, they are harmonic. But you can do other kinds of traps also. Okay, so Elena has shown you already different strategies. For example, if you do this accordion lattice, this is a nice way of producing planes of atoms. And as Elena told you, you can, by moving the angle between the beams, change the distance between the minima, right? Yeah. The mass that appeared there is the mass of the atom. Yeah, it's just that, okay, so what I'm saying is that Okay. So then here, from here to here, you do some mechanics. Okay. So if you have a net, so some matter with mass m, subject to a potential which is like this. Subject to this kind of potential. Okay. So this is actually this is k x. Like you see, I can put this as k, and you know that the particle here will behave as a harmonic oscillator, and you know that it will oscillate in this trap with a typical frequency, which is just this k divided by its mass square root. Okay, and this is the mass of the atom which is trapped there. No, it's not an effective mass. No, it's the mass of the atom. This atom is feeling this potential. This is really a potential. I mean, if you calculate this, you're going to write this in joules. You can calculate in joules, okay? And then the mass of your atom is 10 to the minus 27 kilo. You can put everything and you can calculate. There is no, here h bar is not equal to 1. So here everything is really there, okay? So this is really an energy, okay? Okay, so... Okay, so yeah, so I mean, it's very practical to put h bar equal to 1 if you do some simulations, but I'm experimentalist and I really want to have the thing to calculate right away what's my energy, what I expect from my... So this frequency here that you calculate exactly like this, it's really what the frequency that you're gonna see, so you're gonna measure your atom oscillating. So if you want to measure those frequencies, you just, for example, frequency in the z direction, you turn off your trap, the atoms begin to fall, you turn on again, and then they do, and you see this oscillation, okay? And you measure this frequency, okay? So, okay, then you have this, so you can do, as Elena showed you, this array, 1D array of planes, of potential minima, if you use this kind of strategy, right? If you make two pairs of beams counter-propagating like this, you can do a 2D array of 1D clouds, right? Why? Because let's imagine that if you send two beams counter-propagating, what's going to happen? So you'll have E0 e to the EKZ plus E0 e to the minus EKZ, and then the total electric field squared. If you do the math, you're just going to find that this is equal to, so you're going to have the two cross terms plus cosine of 2 E0 times cos of KZ, yes, that you can also write as E0 squared. So 1 plus cos of KZ is equal to 2 times cos squared of 2KZ. All right? So, right? So 1 plus cos of... I also have a... This is here. This is E0 plus E0. Now if I take the modulus of this, this is also, yes, it's true. Yes, exactly. So this is 2 E0 cos of KZ, indeed, so I guess right apart from this. So this means that for somehow I don't know. So, okay. So, yeah, I'm going to just erase that. Okay, and so, and so this is what you get. And okay, so this means that you have a kind of array of minima, right? And the array of minima, so see if this cos squared of KZ. So this array of minima, every time you have, so this is a cos squared, so every time cos is equal to 0, you have a minimum. So you have a minimum in pi over, when this is equal to pi over 2, and a minimum when this is equal to 3 pi over 2. So this means that the distance between two minima is just equal to it's when kz is equal to pi, so this means that this is pi divided by k, or this is equal to lambda divided by 2. So the minima are separated by lambda over 2. In this case, when they are counter-propagating, of course, in the case of the accordion, you have an angle, so you need to include the angle. But in the case up there, in the A, so they are counter-propagating, so the minima are separated by lambda over 2, where lambda is the wavelength of the light that you use to create your trap. And here you can, if you send the light beams in 3 directions of space, you can create a 3D lattice of point minima, right? So you can do lattices. You can also, by a nice arrangement of beams and by using what we call multi-frequency. So you send beams of light beams of a certain frequency and of a frequency which is the double of that frequency. You can create some other exotic arrangements of minima, like a Kagome lattice, and you can do some condensed matter Hamiltonians. Yes? In general, yes. So if you try to load a lattice like this directly from a vapor, it's not going to be very efficient. Yes, because so the depth is not very high. So normally all those experiments they yes, mud, some kind of initial trap, then they go, yes, there you have some automatic experimental sequence that lasts for some seconds. Yes. Okay. And you can also be still more fancy. So you can go to nowadays you can use SLMs or DMD. So SLM are special light modulators that modulate the phase of the incoming light, or some of them can modulate phase and intensity. And then if you modulate the phase of your light, okay, you're gonna see nothing because the phase makes no intensity difference. But then if you focus your beam light in the focal plane, you can make some intensity modulation, or you can even, you see, diffract laser beams with different shapes in different directions, and you can do all sorts of traps. So those are just the traps related to the results that Hélène shown from Hazibabich group, and also from Jean Dalibard group, this image 2D down here. You can also trap atoms in a 2D potential, and you can also using and then you also have the DMD. So DMD is digital micromirror device. So you have some mirrors that you can let them on or off, right? And so you can remove intensity or not. And when you do this, you can, and then you make the image of this on the atoms, and you can do all sorts of traps for the atoms. So what you are seeing there on those blue images in blue, those are atoms. This is not light. Of course, they're trapped in light, but those are atoms, okay? And so you see that you can do all sorts of traps. Now you can ask yourselves, what kind of physics can I study if I do a penguin trap? And I'm going to say, probably nothing, but it's fun. So this is why they did. And I also have, Patricia also shows her own face done with atoms, but okay, so then... and then this is just, so other things you can do with light. Everything I have said up to now, we are talking about static potentials, okay? So you just let your light there, and the atoms will be trapped in this minimum. But what you can also do, you can also use the light to steer your atoms, right, Helene? And then you can put, or you don't do it. Okay, so how do you steer atoms here? Do you want? So the atoms are... Oh, my sister. Do you hear me? This is done in a bubble trap. The atoms have to live on the surface of an electrode. So I will show you in the seminar. And what we are doing in this experiment, normally the bubble trap is rotational invariant. But first, we break the rotational invariance by tuning a little bit in one direction for making it anisotropic. And when we do it, that we rotate this anisotropic. And And how do they turn again? So it's it, mm. Mm. Okay. Yeah. Okay, because I read in diagonal. I thought you were imposing this phase profile for them to. Yes. Okay. Okay. Yes. Okay. So you can do all sorts of things. So okay. So then this is purely magnetic, and this is in the wrong place. And uses radio frequency, which is, I have not told. So I think I have not. Yes. Okay. And another thing you can also do with optical traps, then it's you can do optical tweezers, which are very fancy nowadays, right? So you can do, well, all sorts of 2D arrays, for example. Now there's a caveat in these arrays. It's differently from. So what's nice is that you can really do all sorts of geometry. What is not that nice is that the distance between the atoms cannot be as close as lambda over 2, for example, because you are making individual wells, and of course you have diffraction limit, etc., etc. So okay, you can be. I'm not sure about the record. You can make, for sure, you can make 2 micrometers. I don't know if you can make 1 micrometer. But anyways, then you have other strategies. If you want to induce some interaction between atoms, you can do some Rydberg dressing that I think you'll heard about next week. But so ground atoms, they will not see each other that much in this kind of situation. But anyways, you can do nice arrays of atoms. You can do 3D arrays of atoms, right? And you can even do some quantum computing. I don't know if you have already seen those kind of fancy videos. Let me see if I can go here. Of this QERA computing. So, okay, so you know.
É mais fácil trabalhar quando você sabe que está tudo em dia.
This is non-related. So I don't want to advertise nothing here. So you see, so those balls are individual atoms, and they are just being moving tweezers. And so tweezers are really like really focused traps, right? And then you are really taking a tweezer and moving your atom around. So you see, you have like a memory, and you have processing for your atoms, and I have really no idea what's going on when they are close by, but I mean they are doing some kind of quantum gate, two qubits quantum gate there, right? And so of course this is for us to see. So I guess that once you image your atoms, you lost all entanglement. So I think it's like every time they do this, the image is not really quantum computation, but it's just for us. This I don't know neither. This is really weird. So it's somehow YouTube thinks it's related to what I have just shown. I'm trying to hypnotize you. So yeah, okay, so this is like optical tweezer. So you see the versatility of optical trapping and magnetic trapping also, okay. I think I don't have much more to say. So, and then I think I'll stop here. And this is everything I wanted to show. And then we can also begin earlier, half an hour. So we have half an hour of coffee break, and then we come back at 3:40. So I thank you for your attention. I have seen that you were paying attention from beginning to end, even if sometimes it was lengthy. I don't know if it was if it was interesting or basic for everyone. I think some of you enjoyed knowing the techniques in details. And okay, if you have questions, you can ask me. Thank you.